Good morning. Welcome to all. Today's topic is production of yarns using false twist principle. Is it possible to employ a false twist principle to produce yarns? Yes, it is possible, and the details we are going to discuss today. Before we go to what is false twist and all, what is a real twist? A real twist is a real twist is produced by holding one end fixed and rotating the other end. We get what is called as the real twist. And what is a false twist? A false twist is one. You hold both the ends and insert twist in the middle. When the twist is inserted by the twisting element in between two fixed ends, then a twist in the upper part, that is above the twister, will be in one direction, and the twist in the bottom one will be in the opposite direction. If you calculate the total twist, then this Z and S twist, they get cancelled each other, and the total twist is 0. In fact, there is no twist at all. But we have already seen this false twist can be employed for many different purposes. We have seen in rotor spinning, the navel, it imparts or it generates false twist, and this helps in getting stable working condition. From the navel to the yarn formation point, false twist adds to the strength of the yarn that is being twisted, and it reduces the end breaks. It makes the rotor spinning very stable without end breaks. Similarly, in the case of speed frame, from the front roller delivery to the flyer top, a false twisting unit is provided, and that rotates the yarn and imparts false twist from the flyer top to the front roller delivery, thus making the strand, already it is twisted, that twisted strand, additional twist is given so that the end breakage rate in the speed frame comes down. So these are the positive aspects of what we call a false twist. But all these are temporary twist. Can this be used to produce a serviceable yarn, a usable yarn? Yes, it is possible, and that we are going to see in detail now. Now, where the real twist, that is holding one end and twisting the other end, it is applied. Obviously, we have seen in rotor spinning, the real twist is imparted in the rotor spinning. If we go to ring frame, the traveler imparts a false twist. By the rotation of the bobbin at the bottom, that false twist is getting converted to real twist. Similarly, in speed frame, even there, false twist is imparted by the flyer. That false twist is converted to real twist by the rotation of the bobbin. So, wherever the twisting element is in between the two ends, delivery end and the winding end. When we twist in between, then we have to rotate the twisting element as well as the element that is going to take the material, like bobbin in speed frame and the ring corp in the ring spinning. In rotor spinning, what we do is, there are no two elements to rotate, only one element rotates, and that imparts the twist, that is a real twist. Now let us look at the diagram. Already we have seen. To recall the idea, we'll see here. Here you can see there is a fiber feed tube, and this in rotor spinning, this is the rotor groove, and in the rotor groove the fibers are deposited, and here the yarn that is already formed, and one end is on the package. That package is a fixed point for our purpose now, and because of the rotation of the rotor, the yarn is formed at this place. So here we can say there is a break introduced, or we can say this is an open end. This open end is one rotating point and the other point is on the package. This is the application of what we can call a real twist, not having two elements to get the twist, that is first element imparting the false twist and the second element converting the false twist to the real twist. That part is not here in rotor spinning. Straight away the one free end or open end is being rotated by holding the other end fixed. Now let us look at this false twist principle once again in detail. Now this K1 and K2 are the fixed yarn holders. Let us assume a strand of material is held between this K1 and K2, which are fixed. The yarn is not moving, that is, this is the yarn and this is the twisting element T. This twisting element, when it is rotated in a particular direction, then it imparts twist in this area in a particular direction, and below this the direction of the twist is opposite. As we have already seen, the total twist between this point to this point, because of the direction, algebraic sum will be 0. Now let us introduce a small change. Instead of being fixed strand holders, let us have rollers which can move the material forward. The direction of movement of the material is in this direction from right to left. You can see here this arrow. So this is the, let us say, the delivery roller, and this let us call, okay, this is the feed roller and this is the delivery roller. Now when the false twisting element is rotated, let us assume the material is also moving. Now if we observe closely, between this region A, there is a twist, the false twist, and when the material moves past this twisting element, this twist gets untwisted, the fibers become parallel. This is what we see in the rotor spinning false twist generated by the draw of nozzle. That is, if you assume this is a draw of nozzle, above this there is a false twist, and after the twist imparting element or the false twist imparting element, the twist gets untwisted. This is an important principle, what is called as false twist principle. All these are already we have discussed, I think in the previous lectures, once or twice in detail. This is only for recalling the ideas. Now this is the false twist principle. How to produce yarn? Let us see another diagram and try to get how the yarn is formed. Look at this diagram. This explains how the yarn is produced by false twist. You can again see here a set of rollers. We can call it the drafting roller, a front roller of the drafting system, front rollers of the drafting system. The drafted material comes here, and this is a twisting element or false twisting element because it is rotating between these two sets of rollers, and this, by its rotation, it creates a false twist in this area. After passing through the twist imparting element, the material whatever has been twisted becomes parallel. This is what we have seen in the previous diagram. What is the difference here? Now let us assume that the drafted material is in the form of a wide ribbon, that is, this width is large. Now when this material comes out and this twist imparting element is rotating or twisting the material, again as we have seen, false twist, that is, these turns of twist are formed in the strand. The difference is some of the fibers escape the twisting action, that is, the false twist is not given to some of the fibers, what we call edge fibers. They escape the false twist action of the twist imparting element. some fibers you can see here, these fibers have escaped the twisting action. They have not been subjected to the twisting action of the twisting element. Okay, it's a big deal about it. Now, when this material comes out, this twisted material in the center, they get untwisted. That is also we have already seen. What exactly is the difference? The difference is these fibers which escaped the twisting action, when they go beyond this twisting element, when the core fibers, that is majority of the fibers, get untwisted, in the same direction this edge fibers get twisted. That is the important critical point. The edge fibers, they don't have twist here, but after passing through this twist imparting element, when the core fibers are untwisted, become parallel to each other as we see here, this edge fibers, they become twisted because along with the fibers, these fibers, they get twisted in the same direction. That is, core fibers by untwisting, they become parallel. These fibers are untwisted, but they become twisted here. So, what happens? So, there is a parallel core of fibers to the extent of 90%, 95% or even something more. About 5% or something still less. These fibers, they cover the parallel core of fibers and they become something like bands, belts holding the parallel core of fibers, and this fibers, they hold the core fibers and we get a serviceable yarn. This is the principle of yarn formation using the false twist principle. You can see here only a very small amount of fibers to the extent of 5 to 10%. They hold the core very tightly. So, this yarn, the yarn produced looks like what has been shown here. You can see these lines, parallel lines, these are the fibers, core fibers, and you can see these are the wrapper fibers, and this wrapper fibers, they provide the stability to the structure. If the fibers, all fibers are parallel to each other, there will not be any coherent structure. If we pull the yarn, it will break. But these, what you call the wrapper fibers, they provide the coherence to the structure here. So, this has a distinct structure, and this type of yarn is called a fasciated yarn. The fasciated yarn, what is the meaning of this fasciated? If we look into the dictionary, we find the meaning fascia is a Latin word meaning band. This band is something like a belt or the wrapper fibers that act as bands on the core fiber to hold them together. So, this is the meaning of the word fasciated, coming from the Latin root fascia. Fascia means band. Okay, this is this yarn. Is it really a yarn? Can we use this yarn? The question immediately comes to our mind is this. Yes, this yarn, though it is not very strong like a ring spun yarn, this yarn has sufficient strength that can be processed and converted into fabrics. What is the advantage? The advantage, we are going to see very high production rates are possible. With very slow moving or tangible components like spindle, rotor, bobbin, flyer, these are all big components that impart the false twist or the real twist. But here in this case, with this principle, it is possible to produce yarns at very high production rates without moving machine components. That is one of the biggest advantages of this process. Some of the machinery that have been developed on this principle are Murata jet spinning, Druff 3000 and Linz. These are the companies that have developed a popular commercially working machines, and these machines have achieved some success. Of course, now other developments have taken over this type of yarn production. We will see later. Now already some machines are running. We will try to explore the machines, important machines that are being used in the industry. The machine that has become highly successful is the Murata jet spinning machine. This is also called two nozzle spinning system. Let us look at the diagram and try to understand. This is the diagram for the Murata jet spinning employing two nozzles. There is another Murata jet spinning which is called by another name Murata vortex spinning, that we will see later. Here we are using the Murata vortex spinning machine works on a different principle. Vortex is also a jet, but to differentiate between these two, Murata company has given the name Murata air jet. This employs false twist principle. Murata vortex we are going to see later, that employs another different principle. Though the air jet and vortex, they mean almost the same. For our purpose, we will call this air jet spinning, and the next machine we call it as vortex spinning machine. In the literature, the vortex spinning machine by Murata is called Murata vortex spinning, and a similar machine developed by Rieter, they call it a Rieter air jet spinning. We will consistently use the word vortex for that type of machine. Wherever false twist principle is used, those machines we call it air jet spinning machine. Now, if you look at this diagram, you can see here the sliver can, that is the feed material is sliver, draw frame sliver, and then you can see the standard drafting system. Only difference is instead of 3/3 double apron drafting system, here we have 4/4 double apron system, that is one zone has been added to give more draft. Then this is the first nozzle and this is the second nozzle. The second nozzle is the main nozzle. First nozzle we can call it an assisting nozzle. This is the main nozzle, and here this is shown somewhere here in this way, and then fourth one, point number 4 is this one, yarn takeoff roller. This one, when here the yarn is being formed, and the yarn that is formed is taken by the takeoff roller. Then there is a yarn suction device, if there is an end break or something like that, suction device, and then electronic yarn clearer. The yarn is immediately after being produced is checked for defects. If the yarn is defective, then it is discarded, sucked by this system, and then finally we get the cross wound package. This area is shown in detail here. There is a drafting system, then first nozzle, second nozzle, already we have seen. What is the working principle? Let me explain the working principle. The feed material is taken from the sliver can 1 in the form of sliver, that is this part. The sliver is drafted to the required thickness by the drafting system 2. The draft given to the sliver is of the order of 100 to 200. In ring frame, the draft is of the order of something like 10 to 50. Here it is 100 to 200, quite a high draft. The draft stand passes through the first and the second nozzle. Air vortex with a speed of 2 million RPM, that is, in other words, 20 lakh in Indian terminology, 20 lakhs. Compare this with ring spinning, 20,000 RPM and 200,000 RPM in rotor spinning. The air vortex is rotating, that is rotating with a speed of 2 million RPM is generated in the second nozzle. The strand gets twisted due to the air vortex. The strand achieves a speed of 250,000. Though it is 2 million, because of the nature of the vortex and the air, all those things, the real twist achieved, real rotation that is achieved on the yarn is of the order of 250,000 revolutions per minute. The compressed air, it reaches the speed of sound when entering the central canal of the false twisting element. This is the false twisting element. When the air enters, the speed of the air is of the order of sound of the speed of the sound, velocity of the sound. When this happens, will the yarn can the yarn withstand this high vortex speed? Fortunately, the axial forces are low during this rotation, and thus the yarn has low tension only. The ability of the air vortex is so high, it is of the order of 2 million. Of course, on this strand it is 250,000 rpm, but again it is so high compared to other systems that the twist in the strand, it reaches the front roller nip, and as soon as the material comes, it gets immediately twisted. That gives stability to the system. The edge fibers that are going to wind as bands are quite few, and for process reasons do not exceed 5% of the total mass of the yarn. Now here, when the material comes out, we don't make any efforts to condense the fibers, rather we want to deliver the fibers in a broad ribbon form. Depending on the width of the ribbon that is delivered here, the edge fibers will be more or less. If the width is small, the edge fibers will be less, and if the width is more, the number of edge fibers that are going to become fascia or the bells or the bands, it depends on the width of the fibers. When the width is more number of edge fibers will be there. These edge fibers are twisted slightly in the direction of core fibers here. Some fibers are likely to be twisted in the opposite direction too. Now, how this is achieved? This is achieved by two factors. Delivered strand is in a broad ribbon form, that is one control aspect, though the realization of the twist in the edge fibers is rather less. Though we are having a wider width that produces edge fibers, the effect is rather less. The first nozzle, that is this nozzle, has an air vortex, the direction of which is opposite to that of the second and the main nozzle. Now here we have 2 million rpm, and here we will be having less speed, and the important aspect is, if we have clockwise direction, this becomes anti-clockwise direction in the first nozzle. This first nozzle has the function of getting the edge fibers to rotate in the opposite direction, and this first nozzle has this very important function. The first jet is weaker than the main jet, that is the second jet. It ensures that the edge fibers do not get twisted in the core fibers. Even make some of the edge fibers to be twisted in the opposite direction. Now, as the strand goes past this second jet, we have seen the second jet and the first jet. Second jet is creating some sort of action on the edge fibers, and as soon as the material comes out, the false twist in the core gets untwisted, as we have already seen, and they become parallel. The edge fibers, on the other hand, which had no twist or low twist or even twist in the opposite direction, get twisted in the opposite direction. The twist generated to the edge fibers bind the core parallel fibers, thus creating a coherent yarn. Already we have seen the principle and how this principle is implemented with the help of two nozzles. The yarn thus produced is drawn by the takeoff roller, passes through a suction device and through an electronic clearer, then wound onto the cross wound package. The two nozzle air jet spinning system has been commercially introduced, and it has achieved some sort of success. Right. Now, what are the raw material requirements for the two nozzle air jet spinning system or the Murata air jet spinning system? In this yarn manufacturing system, only synthetic fibers, blends and combed cotton can be spun. Even the combed cotton strength is rather less, with only about 50 to 70% of the ring spun cotton yarn. This eliminates the possibility of using these yarns in an industrial setup to a very large extent. The fibers should have high tenacity, that is fiber requirements, high tenacity, high fiber to fiber friction, because the strength is provided by the bands. So the fiber to fiber, the core fibers and the wrapper fibers, they should have high fiber to fiber friction, low bending stiffness, because the vortex should be able to work on these fibers, low resistance to twist, that is the fiber should be able to be twisted. Again, this is a fiber property, and small proportion of short fibers. So almost all these are satisfied by the synthetic fibers, strong fibers, and to a large extent these are satisfied by the combed fibers, combed cotton fibers. Now about this length, which is very important in ring spinning. Here also the length is important, in the sense when we increase the length, the spinning properties, all this improves the yarn quality. Trash and micro dust should be minimum. Why? The reason is the air vortex will get disturbed and the fiber yarn formation may be affected rather very easily because of this. A minimum number of 80 fibers in the cross section is essential. What are the yarn characteristics? This is the raw material requirements. Yarn characteristics. The first point is good evenness. Obviously, this is comparable to ring spun yarn, because drafting system is being used. Whatever you can get from the ring spinning, the same level of evenness we can get. Compared to rotor spinning, there is a back doubling, and because of the back doubling, that is better than ring spinning. Here it is comparable to ring spinning only. Then good abrasion resistance, because of the presence of wrapper fibers, the abrasion resistance of the yarn is quite good. Then low tendency to pilling, again because of the wrapper fibers, low tendency to pilling. Then fourth one, low snarling tendency. Again, since the yarn has a very low amount of twist in the traditional sense, the tendency of the snarling becomes acute when there is more twist. This yarn contains a less amount of twist, and shrinkage similar to cotton. Yarn shrinkage or the fabric shrinkage after processing, wet processing, the shrinkage similar to cotton or ring spun yarns. Not cotton, ring spun yarns. Negative aspects. What are the negative aspects? High resistance to bending. The fabric becomes stiff. Then less covering power on the fabric. Covering power. That is, in other words, the yarns are not bulky. Irregular distribution of wrapper fibers. Obviously, because of this wrapper fiber distribution, the properties will be different. Already we have seen the yarns are less strong. Can we increase the strength of the yarn? Yes, it is possible. If we increase the number of wrapper fibers, the strength can, wrapper fibers increase more strength. But unfortunately, if we increase the number of wrapper fibers, what happens is the yarn becomes stiff and the fabric also becomes stiff. As a broad guideline, strength of the pure synthetic and blends with at least 50% synthetic fibers, they achieve about 80% strength of the ring spun yarns. And then technological aspects, draw frame. Draw frame sliber with a linear density of 3 kilotex, that is 3 grams per meter. Usually it is about 5 grams per meter for most of the yarns that are produced in ring spinning. So, here 3 kilotex is preferred as feed material. 3 passages are required in the draw frame to achieve the parallelization of the, that is draw frame, 3 kilotex and 3 passages. Not in rotor spinning, sometimes even a single passage is sufficient. Usually it is recommended to have 2 passages, but for Murata jet spinning, it is recommended to have 3 passages. In the drafting system, the air jet spinning machine is a 4-line double apron drafting system. The draft range is of the order of 65 to 220 in machine, air jet spinning machine. The air pressure in the jets is of the order of 4 to 6 bar. Coarse yarn cannot be produced as the wrapper fibers will not be able to bind a larger core. Binding action can be controlled by raw material quality, ribbon width of the drafted strand, amount of draft given by the drafting system in the machine, yarn tension, air pressure in the jets and twist relationship between the 2 jets. These are the factors that can control the number of edge fibers or binding fibers. With this we conclude today's topic of air jet spinning or production of yarn using false twist principle. Thank you.